Welcome back everyone, Patrick here, moving on to another word problem dealing with exponents. So we're told a certain element has a half-life of 12 hours, and based on that scenario, we got three questions here. So what percentage of an initial mass remains after 48 hours? In part B, if the initial mass is 90 grams, how much remains after 24 hours? And then in part C, we have to write an equation for the mass remaining that contains an exponent that has a base of 2. So with this particular scenario, what I'm going to do is I'm first going to start off with writing out a table. And what we can do is, let's say we have a column here for hours. And let's start with the percentage of a certain mass, because that's what they're asking for in part A anyway, right? What percentage of the initial mass remains after 48 hours? So notice that at the beginning, at 0 hours, we have 100% of whatever that initial mass is going to be. Now, if a certain element has a half-life of 12 hours, it means 50% of its mass decays every 12 hours. So if 12 hours pass, how much percentage of the initial mass is going to be remaining? Well, it's going to be 50%. And then it's going to continue to half every 12 hours. So in 24 hours, it's going to be half of 50%. So 25% of that initial mass would be remaining. 36 hours after, 12.5% would be remaining. And then 48 hours after, 6.25% would be remaining, right? You keep halving it. And so from this table, this ends up being the answer to part A. So whatever that initial mass is going to be, it could be any amount of grams or kilograms or milligrams. After 48 hours of this element, 6.25% of that initial mass is going to be remaining. So notice here, we just worked with percentages. Now, in part B, we're going to be working with an actual mass. So what happens is that it starts off, the initial mass starts off at 90 grams. And so we could just keep going over here, and they're asking at 24 hours, after 24 hours, how much mass is remaining of the 90? Well, after 12, 50% is remaining, so it would be 45 grams. And then another 12 hours after that, it would be 50% of this, which would be 22.5 grams. Okay, another way you can get this is because 25% of the initial mass remains 24 hours, you could take 25% of 90 grams, which would give you that 22.5 as well. Or you could just keep going and halving it, right? If you didn't make this percentage column beforehand. And so the answer, the final answer to part B, ends up being 22.5 grams. Now in part C, what they're asking for is for an equation that shows the amount of initial mass that is remaining. So, and it has to have an exponent too. Now we've done half-life questions before, but remember that exponent was always had a base of a half. So that's what I'm going to first start with, and then I'm going to convert it to be a base of 2. So let's introduce some variables here. So we'll let m equal the mass remaining. Now in part C, we're not given an initial mass. Notice in part B we were given an initial mass of 90, so I'm going to introduce another variable, and I'm going to let I equal the initial mass. And from there, what we can do is we can create an equation. So what happens is the mass remaining is the initial mass, and what are you doing to that initial mass every time, every 12 hours? Well, you're multiplying it by a half, so you're going to just continue to multiply it by a half. And then the exponent that you're going to use, you actually have a couple of choices, and I've gone through this in previous problems before, where we can either allow this exponent, we can let the x equal the number of 12-hour periods that have gone by. So if we let this be, let's say, number of periods, or number of 12-hour periods. Let's create another column here. So initially it's just 0. Well, the first 12-hour period means 12 hours have gone by. The second 12-hour period means 24 hours have gone by, and then 3, 4, etc. So we could let x be this. So we could let x equal the number of 12-hour periods. And that's an easier exponent to deal with because we can just then put that x in the exponent like that. And notice that you could test this. So for example, let's say we go back to this scenario. So the mass remaining, the initial mass would be 90, and it would be 1 over 2 to the power of the number of 12-hour periods. So the first 12-hour period, we would plug in 1 over here, right? The first 12-hour period is just an x value of 1. So notice 1.5 to the power of 1 is just 1/2 times 90 would give us 45. What about 2 12-hour periods? Well, we could plug in 2 for x then. And if we plug in 2 over here, we have to do the exponent first, right? So we would do 1/2 to the power of 2, or another way to see this is just 1/2 times 1/2, like that. So we would do 1/2 to the power of 2, which would be 1 over 4, or 1 over 2 times 1 over 2 gives us 1 over 4, and then 1 over 4 times 90 would give us that 22.5 over here. And you could just keep going, right? So that is one way to make the equation. We can let x equal the number of 12-hour periods, but we can also, I'll introduce a different variable. You could also use x. I'm going to use t just to switch it up. We could let t equal the number of hours that have gone by. And then the exponent then is going to be a little bit more complex. What you would have is m equals I, 1 over 2. And then you can't make this exponent just be t over here, because if we let it just be t, what would happen is, let's say 12 hours after, if we plug in 12 over here, notice that we wouldn't get the correct mass remaining. So for example, going back to this scenario, if we plug in 90 here, we'd have 1/2 to the power of 12 over here, and that wouldn't give us that 45 grams. So how can we get an exponent? We know we have to have an exponent of 1 here when we plug in a t value of 12. Well, what we can do is we could just take that t value and divide it by the half-life period of 12. Right? So notice that if we plug in 12 over here, 12 divided by 12, it would give us that exponent of 1, which if we use that 90 grams as the initial mass, it would then give us that 45 grams after we plug in 12 for t. Or if we plug in 24 for t, 24 over 12 would give us an exponent of 2. 90 times 1 over 2 to the power of 2 would give us that 22.5. Right? So if you're letting the variable in your formula be the number of hours, you got to always just remember to divide it by that half-life period, right? Whatever it is. In this case, it's 12 hours. Versus here, if we let x, or we let the variable be the number of 12-hour periods, then we don't have to worry about dividing this by anything. Okay, the exponent can just be by itself like that. Right, so those are two different possibilities for the formulas. Now we're not done yet, because remember, we can't have a base of 1/2, we have to have a base of 2. That's what the question specified. Well, notice that 1/2, if we just look at 1/2, that's the same as what? Well, 1/2 is like 1/2 to the power of 1, and then we can bring this up, and then the exponent would change to a negative, so it would be 2 to the negative 1, right? Just in general, a to the negative x is equal to 1/a to the x. That's a rule right there. So if we have 2 to the negative 1, right, it would equal 1/2 to the power positive 1, which would just be 1/2. So it's like we're going backwards. We're going from the 1/2, putting an exponent 1 there, bringing it up, and then the exponent changes to a negative. And so the way we would adjust this now is we would have I times 2 to the power of -1 to the power of x, like that. And then notice these, another exponent rule here. If we got like a to the power of x to the power of y, we can multiply these two exponents and it will just be axy. So then in this case, we can just multiply those two exponents and we'd have I times 2 to the negative x. So that's the formula right there for the mass remaining, where the base is 2. And then same thing over here, we would change the 1/2 to 2 to the -1, and then the -1 we can multiply by the t/12. So basically we'd end up with I 2 to the power of -t/12. For these, you could also put the exponent on the outside. It doesn't matter whether it's on the inside or on the outside. You might see the solutions have the exponent on the outside. The 2 is just by itself in this bracket, so it doesn't really matter, right? You have to do this exponent work first anyway before multiplying by that initial mass. All right, so these, let me just include that x over here. Those are the two formulas for the mass remaining, depending on what you let the variable be, the independent variable that you're working with. Right? If you let x equal the number of 12-hour periods, it would be this formula. If you let t equal the number of hours, it would be that formula.